In science, we talk about accuracy and precision. In a lot of fields, you think of these as the same, but it's actually slightly different, especially in the scientific world. Accuracy is how close something is to the accepted value, and precision is how close your measurements or calculations are to each other. A common way of showing this is a little targets. Over here, you can see that all of the shots taken here were close to the bullseye. They're accurate, they're close to the accepted value, but they're not all really clustered together. The person just kind of shot around there. Over here, you can see that all of the shots are taken really close together, but they're not in the bullseye, they're off. So they're very precise, they're close to each other, but they're not accurate. Over here, don't know what happened to this person, but they're all over the place. The shots are not close together, and they're also not all close to the bullseye. There's one kind of, but not that great. And here we have all of them close together within the bullseye. It's both accurate and precise, and that's what we're going for in science. Sometimes in science we have to use very precise measurements and we need a way to record them, so we use something called significant digits. Significant digits, also called significant figures or sig-digs or sig-figs, so many names. Significant digits tell us how many of the numbers we actually care about. Significant digits are digits that help you determine how accurate a specific measurement or data is. Data are, because data is plural. English. I'm going to list 6 rules for significant digits. Number 1, all numbers that are not 0 are significant. Here's an example, 56.7293. You can see there are no zeros. No zeros means all of the numbers are significant. So we just count up all the numbers we have here. We have 6 numbers in this whole thing. So that tells us there are 6 significant digits. Number 2, zeros that are between non-zero numbers are significant. So here we have a 0, and here we have another 0. Pretend that looks normal. Those zeros, since they're between non-zeros, they're significant. They count. So all of these are significant, all the numbers here. All of the zeros are significant, and there are 5 significant digits. The next one, 3. Zeros to the right of the decimal, I guess this is my right, your right, of the decimal are significant. We'll get to the exception in the next rule. So if you have a non-zero digit, then a decimal, and then zeros, that means we took the time to measure out that far, to measure that precisely. So all of these zeros are significant, and there are a total of 4 significant digits in this number. Number 4, zeros to the left are insignificant. They're placeholders. These zeros here are just placeholders. They're just to show how small the number is. So these are just placeholders. They don't count, but the 4 and 5 count. They're significant. So there are 2 significant digits. Like I said, the zeros are placeholders. Number 5, zeros in the coefficients of scientific notation are significant. That's why we bothered to write them. The 10 is always there, but that doesn't count. That's not what we're looking at. We're looking right here. This is your coefficient. Whee! So that's what we're looking at. If we take the time to put a 0 in the coefficient, that means it's significant. 4.0 times 10 to the 8th equals 400 million, but this is a shorthand way of doing it. This tells us how precisely we know the measurements. We took time to measure it to the 10 millionths place. We measured these first 2 numbers, so we know they're significant. So that's why we write it in scientific notation. Number 6. Zeros in large numbers with no decimal are not significant. They're just placeholders. So if we have no decimal point here, and we have some trailing zeros, that means that those zeros are not significant. Again, they are placeholder zeros. So only the 5, 6, 7 count. So there are 3 significant digits. Counted numbers and exact conversions have infinite significant digits. Exact numbers, such as the number of people in a room, have infinite significant digits. Right now there is 1 person in the room, and that would be me. So there 1.000000 out to infinity. There are no other people in this room. I guess unless you believe in ghosts. But let's not go there. There are 100 years in a century. There are 1,000 years in a millennium. 2 atoms of hydrogen react with 1 atom of oxygen to make 1 molecule of water. A calculated number cannot be more precise than the number from which it was calculated. When it comes to addition and subtraction, we just look for the least precise decimal point, whichever was measured to the least precision. What we do here is we have our problem, and we're going to line up our decimal points. So pretend that looks lined up. Then we get an answer here, But we didn't measure all of these measurements all the way out to the thousandth place. We measured this one out to the hundredths and this one's out to the tenths place. So since this has been measured out to the least precise place, we're going to stop at the tenths place. So our final answer will only go out to the tens place. Our final answer will be 222.1. When you have something like this, you get this big long answer, but 4009 only goes out to the ones place. So our final answer needs to stop at the ones place. Now when this happens, we have to round it. We always round the last number. Up here, we had 222.1. Since we rounded it to the tenths place, we use whatever's the next number to round the number that we're actually keeping. Now here, it's a 0, so the 1 stays the same. If we had something like this, where our final answer gets cut off right here at the ones place, see the next number, the first number we cut off, is a 9, so it's going to round up that 8. Our final answer is going to be 4059, not 4058, because we rounded it up. The 9 rounded the 8 up. When it comes to multiplication and division, we just look for the least number of significant digits. It doesn't matter if it's out to a tens place or a ones place or whatever. It's just whichever one has the least number of significant digits. So we have something like 23.0 times 500 times 9.0008. That gives us an answer of 103,509.2. Now, here we have 3 significant digits, and here we have trapped zeros, so we have 5 significant digits. But notice in the 500, there's no decimal, so those zeros are just placeholders, and this is just 1 significant digit. So our final answer will only have 1 significant digit. We take our first number, and we round it up or down based on the next number. The next number is 0, so the 1's going to stay the same, and our final answer is 100,000. Let's do some practice. If you need to, you can pause to see if you can figure out how many significant digits are in each of these. There's no decimal point here, so these zeros are just placeholders, and this has 1 significant digit. Here, there is a decimal, so these zeros are significant, and there are 3 significant digits. Here we took the time to write out zeros after the decimal and after our significant digits, so there are 5. Here we have a trapped 0, and we have a trailing 0. Since it's after the significant digits, we know it's significant.
And we have 1, 2, 3, 4, 5, 6, 7 significant digits.
Here we have a bunch of placeholder zeros. All these zeros are placeholders, and only these numbers matter. 3, 8, 5 matter, so there are 3 significant digits. Here again we have placeholder zeros, and we have a trapped 0. That trapped 0 is significant, but the placeholder zeros are not, so we have 4 significant digits. Here we have trailing zeros and a trapped 0, so this little 0 between non-zero numbers counts, and these other zeros are just placeholders. So we have 4 again, 4 significant digits. Let's do some practice math problems. So here we have 4.35 plus 8.1. If we do the math, that gives us 12.45. However, the 8.1 only goes to the tens place, so we're going to cut off our answer here. But the next number is 5, so it's going to round up the 4. Our final answer will be 12.5. Next we have 45.0 multiplied by 878.9. If we do the math, that gives us 39,550.5. However, we have 3 significant digits here and 4 significant digits here. This is less, so our final answer will only have 3 significant digits. So these 3 are significant. But the next number, that's a 5, so that's going to round up this 5. Our final answer is 39,600. See, we have 3 significant digits, we have our placeholders, and that's our final answer. We also have 42 minus 5.4. That gives us 36.6. But our 42 only goes to the ones place, so our final answer only goes to the ones place. And the 6 will round it up, so we get 37 as our final answer. Now with division, we have 62.7 divided by 31. If we do the math, that gives us, and on and on and on, depending on how big your calculator is and how many digits it shows. But we have 2 significant digits here and 3 here. So our final answer will only have 2 significant digits right here. Cut it off there. The 2 is less than 5, so it rounds down. So our final answer is 2.0. Any measurement will have a certain degree of uncertainty. We can estimate one digit further than the level of precision of the instrument. So we can estimate the size of this gummy to be 1.53 centimeters in diameter, but not 1.534729.533. This ruler is not that precise. We don't have access to that level of precision. Any measurement will have a certain number of significant digits associated with it that show how precise it is. We don't have inaccuracies.